How can something weighing hundreds of tons, made from metal and carrying hundreds of passengers, rise into the sky? The answer begins with something we cannot see: moving air. Air may appear empty, but it has mass and pressure. When we control how it moves, we can create powerful forces. These forces allow aircraft to fly, racing cars to grip the track, and many everyday devices to work. In this investigation, we are going to explore one of the principles that helps us understand these effects, Bernoulli's principle. We have built a model aircraft wing and created our own airflow test system. Our aim is to measure what happens to the pressure around the wing and investigate how changing the wing's angle affects the result. To simulate the airflow experienced by an aircraft during flight, we are using a leaf blower to create a stream of air over the wing. The wing remains stationary, but the air moves past it. From the wing's point of view, this is similar to an aircraft moving forwards through the air. We are not simply observing the wing, we are measuring what is happening using a data harvest differential pressure sensor. A normal pressure sensor measures pressure at one location. However, a differential pressure sensor compares two pressures and measures the difference between them. One tube is connected to a pressure point above the wing and the other to a point below it. If the pressure above the wing becomes lower than the pressure below it, the sensor records a pressure difference. Acting across the wing's surface, this pressure difference contributes to the force lifting the wing. The second variable we can control is the angle of attack. This is the angle between the wing and the incoming airflow, and it is one of the most important factors affecting a wing's performance. With the sensor connected and the EasySense data logging software, we switch on the airflow and allow the pressure measurement to stabilize. We then record the pressure difference before increasing the wing angle and repeating the measurement. At smaller angles, the airflow follows the shape of the wing relatively smoothly. As we increase the angle of attack, the pressure conditions above and below the wing change. The sensor allows us to see this as a changing pressure difference on the graph. Initially, increasing the angle will generally increase the pressure difference and the wing's lifting effect. However, this increase does not continue forever. If the angle becomes too large, the airflow can no longer follow the upper surface smoothly. It begins to separate from the wing, producing a turbulent wake and changing the pressure distribution. The wing's lifting ability then reduces. This phenomenon is known as a stall. Our small experiment demonstrates the same effect that pilots and aircraft designers must carefully consider with full-sized aircraft. So why can changing airflow produce a pressure difference? Bernoulli's principle tells us that within a moving fluid, such as air or water, changes in speed can be linked to changes in pressure. Where airflow speeds up, its static pressure can decrease. The wing's shape and angle influence how air moves around it, creating different pressure conditions above and below the wing. The wing also changes the direction and momentum of the surrounding air. Together, these effects produce an aerodynamic force. Although the pressure difference in our experiment may appear small, a real aircraft wing has an enormous surface area. Even a modest pressure difference acting across that area can produce a very large force. Bernoulli's principle is not limited to aircraft. A familiar example can be found in spray bottles and atomizers. When air moves rapidly through a narrow opening, a lower pressure region can be produced. The pressure difference helps draw liquid upwards, where it enters the airflow and breaks into tiny droplets. A change in air movement has been used to lift, mix, and disperse another fluid. The same idea was widely used in traditional petrol engines. In a carburettor, air passed through a narrow section called a venturi. As the passage narrowed, the airflow accelerated and its pressure decreased. The resulting pressure difference helped draw fuel into the airflow, mixing the fuel and air before combustion. By understanding and controlling moving air, engineers can make aircraft fly, help vehicles travel faster, and develop technologies that improve the world around us. Thanks for watching. Remember to subscribe to our channel and download your free worksheet from the Practical Explorer tool at www.data-harvest.co.uk.